Homework Hotline, what is your emergency?
Hello, and welcome to Homework Hotline.
Here on the Homework Hotline, we help you with your homework questions. My name is Nathan, and I can help you with math.
So we're a live show, so if you call us, we can help you with your homework in real time. We have a few different ways that you can watch us live. You can watch us on Comcast Channel 22, Prism TV Channel 8007, YouTube Live at Denver DPS TV, Facebook Live at EG Homework, or live stream at livestream.com. Search for DPS TV 22. I'm Sam, and I can help you with science.
I'm Becca, and I can help you with math questions. So you can call us here at 720-424-1666. This is our phone number to get a hold of us. When we're here every Tuesday and Wednesday from 4:30 to 5:30 p.m. So when you call, we can interact with you and help you work through any problems you're having with the questions. If you call in with your math question, I can help you.
Yeah, and on Wednesdays, we also have a science demonstration. Sam over here leads us through some pretty cool experiments. And most of them you can actually do at home with some adult supervision. I hear the weather will change during demo today.
Oh, it could get a wee bit stormy in here. But don't worry, there's no need to grab a little dog named Toto and follow the yellow brick road. Not sure why I had to do that in a Scottish accent, but we'll have more on that later in the show.
Yeah, I was wondering how long you've been waiting to work that in there.
Yeah, just any opportunity. I saw a wee bit, and I was like, it's got to happen.
That word "we" it just made it happen.
So the Homework Hotline is sponsored by Contemporary Learning Academy and Emily Griffith High School. Becca and I teach at Emily Griffith, and Sam teaches at Contemporary Learning Academy.
So for those of you who want to turn in your questions through social media instead of calling, we hear you. We're taking your questions through social media. Why don't you introduce yourself at the social media board?
All right, hello everyone. My name is Jeff, and I'm an intern here at DPS TV, and I'm going to be running our social media board today. So we have a bunch of questions that people have sent in, and as well on the email too. So we're going to be getting to the science questions and the math questions and everything for you guys. So it's going to be exciting.
So what is our what's our trivia question for today?
Well, we have an interesting trivia question, and this is for all you kind of nature people. Here's the trivia question. What is the largest living structure on Earth? Living structure, the largest living structure on Earth.
So it has to be alive.
Yes.
Is it the giraffe? Didn't we talk about that yesterday?
Oh, could be the giraffe.
Probably not.
Probably not, though. You're right. Well, if you have an answer to our trivia question, you can send it in through social media if you want to. But the best way you could get your answer to us is by calling us. We actually have prizes for our if you guess the trivia answer correctly. Our contact information is now on the screen. Phone number I gave to you earlier, that's the same as before, and that'll be on your screen the whole way through the show. But as Jeff mentioned, you can get a hold of us through social media, so send in those questions through there, on Facebook at EG Homework or Twitter at EG Homework. You could text Jeff your questions at 970-680-3771, or you could email them to us at homework@emilygriffith.edu. And as long as you get your questions in by 5:30 today, or maybe like 5:27, we'll get those questions answered for you as we go. So let's start at our social media board. And Jeff, do you have any questions waiting for us?
Yes, I do, as a matter of fact. We have some questions that have been sent in through the email here. There's a question here. This one looks interesting here. It's a lottery question. And it says, my friend prefers to bet the same set of 5 lottery numbers every time. But I say that the probability is the same if you randomly select any set of 5 numbers for the same period of time. Who is right? There's not any concrete numbers in it.
I'm trying to think of a good way to explain this, aside from...
Let's try it together.
Yeah.
Okay, so...
We could break this down into something a little simpler, right? Maybe we can think about... this would be difficult to think about the 5 lottery numbers because the chances of winning the lottery are unfortunately very, very slim. So maybe we could think about like the whole red and blue marble example. And it would be similar to like if you have some number of red marbles, some number of blue marbles. If you take one out and you replace it every time, then the probability doesn't change, right?
Correct.
So maybe we could think about it like that.
But our lottery, and this would be maybe a question of how it works always, is when you take out the number, is it now?
It's
done?
definitely taken out. But what I meant by that was like, you know, in the lottery, you have, I don't know how many numbers, like, what is it, like 60, 70? Or
I have not a clue.
Let's imagine it's 60
right.
numbers.
Okay.
So every time you play the lottery, you have to hit 5 numbers and then the Powerball, maybe if it's the Powerball lottery. In this case, they're saying 5. You have to hit those 5 numbers. So if you pick your 5 numbers, whatever lucky numbers you have, when you play the lottery again, they don't keep those numbers out, the ones that were already picked. All the numbers go back in. So your chances become the same every time. Mm-hmm. So it's kind of like that red and blue marble. We have conditional probability, and then
it doesn't matter which particular number you choose.
Right.
So if you look up maybe on my screen, I was trying to think of a way to visually describe this. So there are 5 different choices for numbers. Let's say, as Nathan said, let's say there are 60 numbers that you can choose from. So that first number there, you're going to have a probability of hitting the correct number 1 out of 60 times. It doesn't matter if you choose your own number or if they choose it randomly for you. Doesn't really matter. And then same idea for the second number. Now it's going to be maybe a probability of 1 out of 59. Same thing, doesn't matter if you choose your own number or it's a random number. And then as Nathan said, every single day that the lottery is drawn, it's reset completely. So those numbers that are chosen for the lottery, they're thrown back into the bin or whatever it is that you're choosing the number for. So it has just as equal an opportunity to be chosen today as it does tomorrow.
You know what I can actually point out? I think one thing that'll be helpful is if we think about, like we talked about yesterday, the coin flipping, and we can talk about like if you flip a coin, so you have heads or tails if you want to go to my screen. Each one has a 50-50 chance, right? So a probability of 1 out of 2 that it's going to be heads, 1 out of 2 it's going to be tails. And I think what a lot of times people mix up is that the probability of like flipping heads is 1 out of 2. If I flip that same equally weighted coin again, the probability of flipping heads on that flip is 1 out of 2 again. But what I think what people get mixed up is like the example you said yesterday of flipping in a certain order, where like the odds of flipping heads twice is going to be what we said yesterday. It's going to be 1 out of 2 times 1 out of 2, which is 1 out of 4. But each individual time is still 1 out of 2, right?
The probability is it's independent. So
that's what I was looking for.
Even if I was thinking of this example of people always do this. So having a boy or having a girl, 50-50 chance, right? So somebody who has 4 boys in a row doesn't mean, now they're going to have a girl because they've already had 4 boys. It means it's still a 50-50 chance between boy and girl. Doesn't matter what happened before.
Right. But if you want to say what are the chances of having 4 boys in a row, then everything is conditioned on the last thing. That everything has to happen in that order. That makes sense.
So I guess a long answer short is it does not matter. The chances are the same if you choose your lottery numbers and you choose them the same every single day, or if you choose random numbers. It really does not make a difference. You honestly, the only way to increase your chance of winning the lottery is to buy more tickets. That's the only way.
But we're not encouraging you to go buy
Not
a bunch
that
of
I'm
lottery
saying buy more tickets.
Clear
Because the
that
chances
up.
are still really low.
So low. So low.
All right. Well, let's go back and get some more questions.
All
That was
right.
an interesting one. I like that.
All right, yeah, let's try. How about this is a kind of a science question here, and the subject.
Kind of science.
The subject is sublimation, and sublimation is when a solid this is the question. It's a multiple choice question.
Okay.
There's a blank, so it says sublimation is when a blank changes directly to a blank. So A is solid, liquid, B gas, liquid, C plasma gas, D solid gas.
Yeah. All right. So it's actually, in this case, it's actually sublimation.
What did I say? Sublimation.
Sublimation.
So that's like
close to like subliminal,
Right,
which
yeah.
refers to like subliminal messages, which is a little bit different. That's about being below the liminal system, but it doesn't matter. Sublimation
Sublimation, okay.
is a term defined as when a solid goes directly from a solid state into a gas state. So the correct answer here is solid, comma, gas, which is D. Is that right?
Yeah, that's right, D.
And some good examples of this, if you just want to think about examples from real life that are fairly common. Dry ice, if you've ever had an opportunity to play around with dry ice, we've done it here on the show. You've got solid carbon dioxide that has to be frozen at a very cold temperature because carbon dioxide doesn't really freeze at any temperature, natural temperature on Earth. So we can create artificially low temperatures and freeze the gas carbon dioxide into this solid block of carbon dioxide ice that we call dry ice. And we call it dry ice because there's no intermediary step where the carbon dioxide turns into liquid form. Under certain conditions, certain pressures and temperatures, we could force carbon dioxide to exist in a liquid state. And we do that sometimes, like if you might have a tank of carbon dioxide. I'm blanking on why you would ever want a tank of carbon dioxide. But if you did want a tank of carbon dioxide, you would keep it under high pressure, and it would be a liquid likely inside of that tank. Another easy example is just to think about clothes that dry outside. If anybody hangs their clothes to dry, some people do this even in the wintertime, and the water from their cold clothes can freeze, and you can end up with sort of an ice sheet. And a lot of times that will just sublimate right off. It won't go from a solid state to a liquid and then to a gas. It'll go from a thin ice sheet directly to gas form into the atmosphere. So those are a couple examples, but sublimation is just that. It's just defined as a solid going from solid state to gas state in one step, skipping the liquid step.
Does it really skip the liquid, or does it just go through it really, really quickly?
Well, I mean, depends on your definition of what liquid and gas are. So solid, gas, and liquid are really about how particles interact with each other, right? So it does go directly to gas state, I guess I would say, because what you have is a solid block, right? And then an individual gas molecule leaving instead of interacting in a liquid state. Whereas in a liquid state, there would be some connection, some form of attraction generally between the molecules in that compound. And this actually gets to some certain types of compounds are really good at making liquids. Some are really good at making gases. Some are really good at making solids, having to do with how well those compounds might attract each other. But no, I mean, we're really talking about a solid sheet of ice, let's say, and an individual water molecule hooked into that solid sheet of ice and then just jumping off. And this happens all the time. It happens in your freezer. And I should say, there might be some other molecules in that same sheet of ice that are turning to liquid. But the sublimating part is just that one molecule that's instantly releasing itself and going to gas form.
Cool. Very interesting.
Yeah.
I had to ask a follow-up. I just had to
No, I
do it.
appreciate it. I appreciate you
Had
asking
to
a
do
follow-up.
All right, let's. I think we have time for another question. Just
okay.
another question before
Well,
it doesn't have to be math.
yeah, it
English
can be,
grammar.
it can be math. You want math?
It could
Yeah, it can be math.
All right, how about this one? This one looks pretty complicated, actually. So it says, if an arrow is equally likely to hit anywhere inside a circular target that is 3 feet in diameter, what is the probability that it will hit inside a bullseye that is 6 inches in diameter?
That sounds like a geometry and probability question.
Cool.
All right.
So I'll take that one. I'm just quickly drawing here a bullseye. And I think one of the things they mentioned, you have equal probability, right? Or an equal chance to hit anywhere inside.
Let's see. Yeah, arrow is equally likely to hit anywhere inside a circular target.
So let me just sketch this out real quick. That is not very centered.
Equally likely meaning
Right, meaning that
your
this person's
aim
not
is not-
aiming
right, their
for the
aim
bullseye,
is not very
right?
good. They're just
Yeah.
hitting towards the board.
Right, exactly.
Like,
That's what I was getting.
Not a
from that.
really good shot.
Right. Like if it was like, I don't know, Robin Hood or something, maybe he has a very high chance of hitting the bullseye.
Right.
He's a good shot, right, Robin
Oh,
Hood?
yeah.
Yeah.
He split
Or
the
if
other
it were
dude's
me.
arrow in twain.
That's right. So he'd be like 100% probability of hitting the bullseye.
Yeah.
But in this case, I'm
Or
going
if
to make,
it were me.
or if it were you, it'd be a
guys
0%.
ignored me.
But, all right. So we want to know the probability of, I'm actually going to erase that color because it's going to be hard to see, of an arrow hitting this bullseye, so the center. And we said that What do we got?
The bullseye is 6 inches in diameter.
Okay, so we got 6 inches here in diameter, and we got 3 feet up here. Now, when we do anything like this, before we even start talking about probability and area of these circles, I want to first think about, we have 2 different units. We have 3 feet in diameter, and we have 6 inches in diameter. So you got a couple options here. I can convert them both into inches or both into feet. So this is really up to you, however you want to do it. I prefer to avoid decimals when I can. So I'm going to convert them both to inches. And I'm going to say this becomes 36 inches. You want to be careful with that, because if you work with the bullseye being 6 inches, and then you say 3 inches or 3 feet for the diameter of the entire target, then you might make the mistake of calling the entire target 3 inches wide, which isn't going to work. So we'll talk about the probability in a minute, but the first thing we want to do is think about, like, what kind of a percentage or what area does that little bullseye make up relative to the entire target. So this is just a surface area problem, and if you remember, the area of a circle, do this little notation, is pi r squared. So here is what I want to do. I want to think about, like, what is the area of the entire circle, and how is that related to the area of that tiny little bullseye? So I'm going to calculate this, and I'm going to say the area of the entire circle, and I'm actually going to do something here really quick, and I'm going to say, instead of just circle, this thing doesn't work that great, I'm going to say the area of the, I'm just going to put big, just so we can do that. And then we want to consider, right now, we said 36 inches, but that's the diameter. So in this case, we're looking for the radius for this equation. So we want to convert this to the radius, which is actually going to be, if you remember, the radius is half the diameter, so it's 18 inches. So we're going to do pi times 18 squared. So I'm going to just calculate this really quick. 18 squared is 324. So 324 pi is the area of this big circle. And I'm going to leave it in this form for a minute. And the reason is because I mentioned yesterday, when we're doing these application problems, it doesn't really make sense to say that the area of the circle is 324 pi. Like, that doesn't really, it sounds weird. It doesn't really have a lot of meaning. Most people would have to. We should. But this is the most precise. Like, if I did this in my calculator, 324 times pi, it would be 1,017.87602. Like, we would end up rounding that, and we're not going to be as precise. And if we want to figure out the exact probability, we want our numbers to be as precise as possible. This is why your math teachers always tell you to leave stuff in fractions and to leave pi in there whenever you can. Okay, so that's the area of the big circle. I guess I could have called it the area of the target. Now I'm going to do the area of the bullseye. Again, it's a little circle, so it's going to be pi r squared. And this said the diameter is 6 inches, right? Yeah.
Yes.
So again, we need to convert this diameter into a radius of 3. So I'm going to say pi 3 squared, which equals 9 pi. So here is what we have here. We have a bullseye that has an area of 9 pi, and we have an entire target of 324 pi. So what we can do is say how did you set this up yesterday?
For probability?
Yeah.
It's
trying to think of like the terms.
It's
outcome you're looking for.
Your outcome over the total possibilities.
Okay. Outcome over total. That's okay.
Yeah.
So outcome over total possibilities. So we want to think about, like, what is the outcome we're looking for? Trying to hit the bullseye. Well, that outcome is only 9 pi inches squared, and the total possibility, and we're including that radius because it's the entire surface area, is 324 pi inches squared. And what you'll see here too, especially for problems like this, is it's kind of nice that I didn't put this in my calculator and put a decimal, because pi divided by pi cancels out. So that's nice. So you have a 9 out of 324 chance of hitting the bullseye, and this can probably be reduced. Actually, yeah, it can be reduced. So we could say you have a 1 out of, let's say 324 divided by 9, 36 chance of hitting the bullseye. So what we're saying here is, like, if you shoot at this bullseye 36 times and you are maybe not a very good shot, you're only good at hitting the entire target, and your shots are equally likely to hit anywhere on the target, you should hit that bullseye in the long run, you should hit it 1 out of every 36 shots.
I like that problem.
Yeah, that's a good problem.
That was a really good problem.
Yeah. Seems like a lot of students are doing probability right now.
It must
A lot
be.
of these, yeah.
Must be. Makes a lot of sense. All right, well, we're going to take a little break, and when we come back, we are going to be working on our science experiment, and that's all I'm going to say. It has something to do with weather, and then that's it. It's a surprise. So we'll see you in just a minute after our break.
We'll start loosening up those muscles for that rub.
Skinology. It's much more than a name.
Really, my company is truly about inspiration. I have a really deep passion and love for skin. I put a lot of pressure on myself to always try to be the best.
Sounds like ingredients for success. Meet Kimberly Shook, the owner of Skinology.
When I say someone that I'm a skin therapist, immediately they're in love with me, which I love.
That love turns into new business.
They want to know where I work, what I do, what I can do for their skin. And so it makes you really proud of your career.
Kim started like many.
I was actually very nervous to start aesthetics school. I'm not the best at spelling or pronunciation.
She succeeded because of the support of the Emily Griffith faculty.
Let's start with the teachers. All sweet, all supportive. I can't believe how much Emily Griffith Technical College has helped me personally and my career. They really invested a lot into me. I really felt it while I was there as a student. And I think because of that love and support, I was able to have more confidence in myself.
Kim's passion leads her.
I wanted to make a true difference in women's lives and in my own.
Now, she's using her education to help clients.
I have so many people that come to me and just tell me that I've changed their life. I really get to watch my clients kind of blossom with this confidence. It's really quite exciting to know that I was part of that change.
But is a facial better than the happiest place on earth?
A client really made me feel really special. I had a wife buy for her husband a gift card. I saw him. He told me I was better than Disneyland.
She's been meeting the needs of clients since 2012.
I actually opened this place while I was in school. I really kind of went from school to here. So I'm a little bit unusual.
What's not unexpected is hard work and dedication.
I never truly have a day off, which is okay because I'm so passionate and so in love what I do. I've been able to open a business for myself. I can do anything I want, right? And I'm not talking about my schedule. I'm talking about that I can truly give back to the community. For Skinology, we do 2 fundraisers a year, and every month we give to a different charity. We have raised and donated almost $10,000 in the 3 years that we have been open. And I'd have to say that's probably my greatest accomplishment, is that I've been able to not only support myself, but I've been able to give back. And that speaks volumes to me.
Hey guys, so welcome back to the Science Lab. We've got a short and sweet science experiment today that I think is kind of fun. We're going to be making tornadoes in bottles or vortexes in bottles and thinking just a little bit about how fluids move. So the first thing we have to do is set up our tornadoes in a bottle. I'm going to have Nate and Becca do the single bottle tornadoes in a bottle, and then Jeff over here is going to do our double one in just a minute for our grand finale. So Becca, here's yours. Nate, here's yours.
Right.
Okay, the fun thing you guys get to do is choose your glitter. Okay. which I know is really
I'm
exciting.
going to take pink.
Yeah, pink for Nate.
Obviously.
Okay. You can. Oh, and actually, you can do 2 colors if you want.
I want purple
Purple.
for sure. And I'm thinking green and purple would be a good combo.
Green and purple. Weird combo, but we'll
Right.
say okay.
Oh, it's going to be great.
I'll go with NA2. I'll take the blue.
Blue. All right, pink and blue. And the reason that we're going to put glitter in is that what we're going to do is we're going to create a vortex or a tornado inside of these bottles. And we just want to be able to see that vortex defined really well. And the glitter is going to help us with that. It'll sort of look like debris flying around the funnel. It'll just sort of give it a little more definition. So, guys, if you could just, these have little sort of salt shaker tops on them. If you could just do a couple shakes of each type. We don't need too much.
Right.
Just a couple.
But there's no, I saw different directions for this that called for like a teaspoon of glitter. That seems really precise when it comes to glitter.
Just got to be careful not to touch it or it will be stuck on me forever.
The only rule with glitter is don't get it anywhere near me.
Never touch it.
Yes.
Is that enough?
That's plenty. That's
I'm putting both in there, right? You said?
Yep.
Okay.
Little of your other color there.
I'm-
Oh, Nate has some glitter on him, so it's over for him.
Yeah, my life is
Glitter
ruined.
disease is going to spread.
You will never get rid of it.
It's true.
All right, look at those pretty little glitter patterns. I don't know if we
So
can see from
pretty.
that. Oh, yeah, we kind of can. So then we can do something kind of fun here that is a little bit unrelated. This is related to the polarity of water. So water has surface tension because the water molecules in this jar right here have a little bit of a magnetic attraction to each other. That's holding the surface together. It's also what the glitter is spread out on. And the glitter is also a little bit, glitter is able to pick up a static charge. So it is also hooked on to the water molecules. Nate, I just need you to put the itziest, teensiest, that's a technical term.
That's a scientific measurement?
Little drop, right.
The itziest,
The
teeniest?
itziest, teensiest little
All
drop
right.
into the center and watch what happens to your glitter.
Oh, wow.
Ooh.
I did not expect that to happen.
So I don't know how visible that was to
ran
viewers
away.
at home. Hopefully it was semi-visible, but ultimately,
We can see it
yeah.
with mine, too.
Where the soap
doing yours,
landed.
too?
Yeah, let's do Becca's also. Let's see if we can. Good.
Sure.
Wonderful.
Maybe just the
see it?
itziest and not the itziest, teeniest this time.
Just itsy.
So that kind of happened in slow motion, and Becca, she didn't put too much in, but that's
Because I
totally
did
fine.
really itsy.
Really itsy. Put a little more, Becca. Let's go just a tiny bit more. Okay, so in any case, wherever the soap hit was somewhere that the nonpolar soap molecules sort of made their own little area. And it's almost like if you put a drop of oil into a cup of vinegar, how it's going to make that little bubble. Now the soap will mix with the water. Soap is a molecule that has one polar end and one nonpolar end. But what's essentially happened is all those nonpolar ends, those non-magnetic ends, came together in the center, pushing all the glitter and the polar stuff to the outside. Anyway, that's not really what we're talking about today. I just thought it was cool. So let's put your lids back on, guys.
So wait, you're saying I got glitter on myself for no reason?
You got glitter on yourself for no reason.
Well played.
No, for some reason. No, for some reason. We got to see the definition here. Okay, so I think what we'll do for full visual effect is we'll have one of you guys go at a time here, and then we'll put your bottle up, and we'll just talk a little bit about it.
All right.
So let's just first see what the effect is, then we'll talk about what it is, then we'll do it again. So Nate, what you need to do is you're going to flip your bottle upside down. And is that
Sure,
lid
it's
on
closed
tight?
all the way.
Yeah, sorry.
I'm
let me say,
double-checking that.
tighten the lid, flip it upside down.
I was like, is there some sort of magic trick that the glitter holds all the water in?
Ta-da! Okay, so now shake it up a little bit just so we make sure we get the... Okay, beautiful. That's perfect. That's just lovely. Okay, so... Oh, that got much cloudier than I wanted to get. Okay, let's see how this works. So Nate, you just need to make a circular motion with the bottle, like
This?
that. Yeah. Mm-hmm. Can I maybe demonstrate for you? That looks
Okay.
like it might be good. That's pretty good, Nate. What you want is a little bit more like this.
Oh, okay.
A little bit more like that. And what we should get is a beautiful vortex. We might have put too much soap in this one, Nate.
Yeah.
Okay, well, we're going to let Nate's hang for a minute. Becca,
Mine will be better.
let's have
don't
you
worry.
not
we'll
shake
see.
it as much. That may have been my fatal flaw. Let's have you go like that. Okay, Becca,
move
can
this
you
out of
do
the way.
the swirl?
You can kind of see it start to form.
And then as you stop, you should be able to set it down, and it should...
No, the green one.
Ah, the green one.
You get that green out of the way there. Look, there's a tornado.
And now if you let it go, Becca, if you just hold it still. Yep, so what Becca did was create, and I don't know how visible it is in there, but Becca's...
Oh, now it's... you
Did
can
it
see more a
disappear?
little bit, yeah.
Try it again, Becca. See if you can get, because it really will create sort of a tornado funnel in the middle, but it won't really appear until you stop shaking it. So what Becca's doing is creating some circular motion just with her arms, circling the bottle around. That's causing all of the liquid to spin around. And then what's going to happen is as the liquid tries to settle down, as the liquid tries to pour toward the center, it'll move around the bottle because of Becca's circular motion. And this sort of imitates the effect that the rotation of the Earth has on wind patterns, which is what causes tornadoes on Earth. Yeah, we're just not getting quite the visual payoff that I want here. Yeah, you can kind of see it in there.
You kind of see it forming a little bit later last time.
So
Like
anyways,
with glitter, it looks like dust or something, or debris, or
and I wonder what it is that made the water so cloudy. I didn't have this experience.
could
at
be
home,
the
I
type
wonder.
of soap maybe that you used.
And maybe that is. All right, well, let's do this. This one is slightly better. So if you have two 2-liter bottles at home, you can. Nice.
That lid is not very.
Yeah, maybe just
It's
flip
not
it.
very flat. Is the problem?
No worries. So
my fault.
if you want to make a double bottle at home, they actually sell really cool connector pieces that will allow you to screw both bottles into it and then make an instant tornado in a bottle. We're doing the sort of DIY easy version. I drilled a 1/2 inch hole into the lid of one of these bottles and then taped using gaff tape, which is probably not the best kind of waterproof tape, the two bottles together. So there's just essentially a little funnel piece. If we just flip these upside down, the water would just pour from one bottle into the other. But if we flip them upside down and add in a little bit of centripetal force, we should get a much better vortex. Jeff, you think you can help us out with this one?
Yeah, I
Okay.
think I can.
So go ahead, flip it over, and you're going to get a little bit wet, so watch the computer behind you. Fantastic. Go ahead and start that circular force, and then give it a sit down, and let's see what happens.
Centrifugal force.
All right, can you guys see it? Kind of keeps disappearing.
yeah,
appearing.
there it goes.
But that right there is a fantastic
Wow.
vortex. And really, the vortex is formed better here because what you have is water coming out of the bottom, creating this little vacuum. And then as the water spins around that vacuum, right, all the water wants to go down the hole, but because of the centripetal force, a lot of the water is pulled to the right, or whatever direction it was that you were spinning it. And so that's pulling all the rest of the water around with it. Should we do that one more time?
Yeah.
Because it was
Yeah.
kind of cool. All right, you did it perfectly, Jeff. Let's just have you do it
Okay.
one more time. And I don't know how well we'll be able to see with the green bottle here, but hopefully it'll be a similar effect. All right.
Yeah.
Oh, yeah.
I see it.
Tornado in a bottle.
Yeah, there it is.
Safe way to experience a tornado, actually.
There's Dorothy's house.
Yeah, there you go.
That's pretty cool.
Yeah, you could either do this or just move to Oklahoma.
Right, or just move to Oklahoma.
guess
Not a
we'll
safe
find
way,
it.
but another
Yeah.
way to experience
A lot of
tornadoes.
options.
And it's one of those kind of like simple science tricks that I think is just a lot of fun for all of us. Like I want you to flip it again because I really like the way it looks. But it's very easy to do at home.
gonna
Strongly
try it.
recommend giving it a shot. And just a small other thing to mention, that centripetal force creating this sort of a vortex. Nice job, Becca. And there's like some piece of plastic in there that's spinning
yeah.
around.
Oh,
It's
it's
kinda
stuck right
cool.
in the middle.
Could
pretty
you
great.
put things in this?
Yeah, you
and
could put
just
any
watch
kind of
them
thing
toss
A miniature
around?
cow, maybe?
Yeah, a miniature cow, maybe someone's house,
That would be
someone's
way
car.
fun. That would be way fun.
This just sounds really morbid, but it still would be cool to watch it in the mini version.
Yeah.
Okay, great.
Cool.
Well, I think we will call that good for today. So that was just our little lesson on vortexes and fluid motion. So thanks so much for joining us here at the Science Lab. We're going to be back in the Homework Hotline studio in just a minute.
There's times when you wander and ponder all the labels you've received.
Believe me, I've got a few. never mind from when, why, or how.
'Cause now, everything's different. I found the perfect place.
A space where the labels fade and I'm accepted and supported.
Check what the news reported. Emily Griffith helps all who wish to learn.
Turn towards your future while you finish the basics on your time.
Prime opportunity in this mature environment.
The only requirement is motivation and thirst for success.
Invest in your passions. There's no limit to how far you'll go.
And know that you'll have something in common with everyone here.
We all chose empowerment over standing still in fear.
Hi, welcome back. Thanks for joining us again on Homework Hotline. I hope you enjoyed the science experiment. If you are just joining us, we'd like to give you our contact information in case you have some homework questions that you need answered today. The phone number is, again, it's on the top of your screen. You can always see that up there, and that really is the best way to get a hold of us. However, we do have our other ways via social media, so you can get in contact with us on Facebook or Twitter at EG Homework. You can text in your questions, 970-680-3771, and then you can also email those questions into us at homework@emilygriffith.edu. So you still have a minute to get those homework questions in, or at least until 5:30. And then also we have a trivia question that you can answer for a prize. So that we have until 5:30 as well. Could you tell us our trivia question one more time, Jeff?
Yes,
Please.
I can. The trivia question for today is, what is the largest living structure on Earth? Largest living structure on Earth.
All right.
Just for a hint and a clarification there, largest living structure, not largest living organism. So maybe think about it from that perspective.
Okay. Well, if you think of an answer, you still have about 20 minutes to give us a call. Again, we are giving away 2 symphony tickets, which I am going to take, and I keep telling everyone
She's been
this.
trying to take him every day, but
I'm going to do it.
She can't have them if you call in.
It's right. It's true.
so ruin Becca's weekend.
Ruin
Call
my
in,
weekend.
get
Come
an
on,
answer.
guys. Do it. All right. Well, I think we do have some more questions on social media that we can get answered. Is that right, Jeff?
Yes, it is right. And we have, we're going to go to Facebook this time. We had, actually, it's interesting. One of our producers was asking an interesting question. So they posted on here. Let's see. It says, sometimes when I microwave a mug of water, I pull out the mug of water and put a tea bag in it. As soon as the tea bag is in the water, it starts to bubble like it's boiling. So why does this happen? Why?
Yeah. Okay, so the easiest way to say this is I don't know for a fact, but I'm gonna make a stab at it. So what I'm guessing is so if I'm reading the question right or hearing it right, my understanding is that you've got water that's very hot at this point. Let's call it pre-boiling water. It's not bubbling when you pull it out of the microwave. And then I guess when you drop your tea bag into the cup of water, the act of the tea bag hitting the water is what seems to make the water bubble up. So this is my guess, and again, I could be wrong. But my guess is that since you're heating, you mentioned specifically that this is done in a microwave. When we heat water on a stove, we do it through convection, and so the boiling is very obvious to us. Convection is a form of heating something where you heat from the bottom, and then the transfer of heat within some kind of a fluid, like a liquid or a gas, in this case liquid water. The heat from the bottom of the pan is transferred up to the water at the top of the pan via convection. So water molecules hanging out at the bottom of the pan will get hot as they're in contact with the steel that's getting hottest. They will rise because they are now less dense. They will rise toward the top of the pot of water. The cold water on the top will pour down the sides to the bottom of the pot, will get heated there, and you'll have this cycle of hottest water rising and cooler water sinking And we call that cycle convection. It happens literally all over the place. It's happening inside the Earth right now. It's what causes plate tectonics. But microwave heating is slightly different. So microwave heating is going to be, so in your microwave, essentially what's happening is energy rays, low frequency energy rays, are being shot at your food or your drink, your water in this case, and high frequency. The high frequency energy rays that are being shot at your food that's actually jiggling the molecules of the food or the water in this case as those waves hit the molecules. And it's the jiggling of the molecules that makes them hotter. A way to think about heat and temperature is slow-moving molecules represent what we think of as cold temperature, and faster-moving molecules represent what we think of as hotter temperature. So the microwave acts to speed up the molecule interactions by knocking those molecules around with these high-frequency waves. So my guess, which could be so wrong, is that when you pull a glass of water out of the microwave, the individual molecules have been agitated to the point of being very warm. They're moving quickly, not a movement that we can see, obviously. So the cup of water looks totally still. And my guess is that I mentioned earlier in the science experiment that water has this polarity. It has a positive end and a negative end. So these individual water molecules will tend to hook onto each other using this magnetic force. And that's really what makes them liquid. It's sort of the hooking on and unlatching and rehooking onto another water molecule. What makes water a gas is when one of those molecules totally breaks free from that magnetic pull and sails off into the atmosphere on its own. That's what steam is, those individual water molecules floating up that have really given up those magnetic interactions between the other water molecules. My thought is that there's a level of surface tension, of magnetic connectivity between these water molecules in your cup, and that when you drop your tea bag into them, you're breaking some of those bonds, thereby allowing some of those water molecules to, what is the word I'm looking for? To evaporate and become steam. That is my guess. Again, it could be wrong. I'd love to have some time to think about it. I love questions like this. Not that I'm great at answering them, but I do think that they're really interesting. Keep sending them in, and if the person who asked this has an alternative theory, or if anybody else has an alternative theory, give us a call or a shout out on one of our social media sites.
I love it. It definitely sounds, at least, that it's you're backing it. You know,
I'm backing it with an explanation. I'm making it sound like I know what I'm talking about.
You're backing it.
You know what, though?
I believe you.
I mean, that's what science is, right? You notice something, and you're like, why does this happen? And you think about everything you know, and then you might come up with like a hypothesis, and then you might test it somehow.
And I'm comfortable in the company of many great scientists who figured out lots of stuff and thought and misunderstood so much else.
Right.
There are all these people that we see throughout history. Isaac Newton had a great understanding of a number of things, also was totally convinced that he could turn lead into gold.
And he never did it.
Well, no, he did not. Alchemy is not really possible at that level.
Darn. All right. Well, let's see if we can get any more questions answered.
All right. Let's go back to the board here.
All right.
And see what we got here. We got another number of questions in here. Let's. How about we do a math question? I have one here. This is a factorial question.
Factorial question.
And
okay.
it says 5 factorial times 5 factorial.
Okay.
What does that equal?
Okay. So, well, first, I mean, maybe, and you might notice the symbol on my screen, that exclamation point is actually, that stands for factorial. So let's actually break down what, I'll write that word out, factorial. What a factorial is. If I have 5 factorial, what that really means is 5 times 4 times 3 times 2 times 1. And, well, we can actually figure that out. So, 6 times 20, so 120. So 5 factorial is 120. And really, any factorial, that's kind of how it works. And it's factorial, right?
It is.
Factorial?
Yeah.
I was literally just wondering that. I was like, have I been saying that wrong?
I've been saying. Okay. Oh, God. Factorial. Anyways, so what that means is just we're multiplying the consecutive numbers all the way down to 1. So if I had 6 factorial and I just skipped 3, oh my goodness. That's what happens whenever you talk and write and think all at the same time. Multitasking, my
harder
goodness.
than it looks.
It is. So 6 5 times 5 times 4 times 3 times 2 times 1. So these factorials actually have values. And what they're really used for is for probability, different types of probability problems where the handshake problem is the one that I'm thinking of.
Yeah.
How would you describe the handshake problem?
I know it's something about like you have to shake everybody's hand in a room, but you've shook one person's hand, so that person's no longer
right.
So that's why you keep reducing it. Mm-hmm. That's like, so how many times would you shake hands
if you had to shake hands with every single person in the room? So if there were 6 people in the room, and really you might subtract 1, so you would say 6 minus 1 factorial. So if there were 6 people in the room, the first time you shook you would shake 5 people's hands.
Actually, I think I should rephrase that. Isn't it something like if you wanted to shake everybody's hand in a specific order?
Yes.
Right. That's where factorials come from.
Yes.
It's really related to conditional probability.
Yep.
Where everything has to happen. Like we talked about heads and tails. Like you want heads, 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 tails, tails. That would be an example you might use it.
It's very true. So if we are doing factorials, so 5 factorial, the question back to the original question was 5 factorial times 5 factorial. So we know that 5 factorial is 120, just because I found that already. And then 5 factorial, again, is going to be 120. So we're going to say 120 times 120, or 120 squared. So I'm going to go for the calculator on this route. And we get, I should have known that. Come on. And that would be what 5 factorial is. But that is, if you ever see that exclamation sign in math, that's what it means, is a factorial. It's actually a mathematical symbol. All right. I think we have time for another question.
Another question?
Let's get another question.
All right. Do you guys prefer science, math? What do you guys have?
We can do science.
All right, yeah, let's do science. Let's
renewable energy. I'll do that.
I have a. Which one is it?
Renewable energy.
Oh yeah. Let's do renewable.
See a little 3 up.
Oh.
Nope, couple down.
Right.
Up. That's science.
Right there. Oh yeah. This is good. Okay. So what is a renewable energy source from the power of water?
Oh, yeah. So the probably the one that's being talked about is hydroelectric power. Well, hydroelectric power is a general term for electricity produced from water, but generally we think of hydroelectric power as being from dams, so hydroelectric dams. So really classic examples of these would be like Hoover Dam in Arizona or Utah? It's in
Nevada.
Nevada? No, Nevada. There we go. The Colorado River flows through Utah and then Arizona, but then in Nevada where Lake Mead is, and at the end of Lake Mead is the Hoover Dam. And so the Colorado River, as Lake Mead, this lake at this endpoint of the Colorado River, filters through the Hoover Dam. It turns a gigantic turbine, and the turning of that turbine creates a lot of electricity. And a significant amount, actually, of the electricity for Las Vegas is produced from, I should look up at some point how much electricity Las Vegas gets from the hydroelectric power. But it's interesting, any type of electricity, or most types of electricity that we produce, it's almost always produced from turning a turbine in some fashion or another. What we really need to do is spin a turbine really fast to create electricity. That is what a turbine is, essentially a generator of electricity. And so dams work great for it because the power of water pushing against gigantic blades can really make these turbines spin very quickly. I'm trying to think. So the other type of renewable energy that I was thinking of was tidal power. So there are power plants that have been set up on the coasts that are able to take power from the tides. And I think that works in a similar way where essentially tide power turns turbines, but I'm not 100% sure of that. Typically, though, when we're talking about a renewable energy source from water, we're talking about rivers providing hydroelectric power through dams.
Very interesting.
Mm-hmm.
Okay, let's go. I think we could do another question.
Another question?
I do.
All right.
I think we can.
Let's
Another
do
science
We're getting these all
Well,
10.
we were talking about tides in that last answer, and then somebody has an actual tide question here. So let's see. It says, what is the spring tide? And it's got a multiple answer. So what is the spring tide? A, tide that occurs when the moon, sun, and earth are not in alignment. B, tide that occurs when the moon and sun are aligned with earth. Or C, tide that occurs during the spring months.
Let's see. So, oh geez. I'm going to need just a minute to think on the tide question. Can you guys come back to me in a second?
Yep,
Can we do
sure.
a math one?
Yeah, we'll do a math.
Yeah, we
And
can do
I'll
that.
think about how to explain it.
All right, let's
Yes,
see.
we
Let's do
can.
a math one. Let's see. Oh, okay, here's one. Here's a math question. A measurement of the percentage of energy consumed that actually performs the desired work is called.
That might be a
Is that
science
a
question.
science?
I think
Oh,
it's
okay.
I know. It's like, I do.
All right,
No.
let's see. Let's find another one.
I totally missed it. What was it?
There's a physics question.
Oh, I
It,
guess
does,
we'll do
it
that
did
one.
seem like a physics question, yeah.
Yeah.
Which can be math. I mean, physics and math, let's be real, they are very, very tied
Right.
together.
Okay,
That is for sure.
here's a math one. How many positive whole integer numbers containing no zeros have the sum of their digits equal to 4?
We'd have to think about
So
that
could
one.
you say that one more time?
Okay, yeah.
We might need to think about that one as well, or at least think of an efficient way to go about
Yeah,
it.
without just testing a bunch of digits.
Okay.
So tell me one more time.
All right, it says how many positive whole integer numbers containing no zeros have the sum of their digits equal to 4?
Integers, no zeros.
No zeros and have the sum of their digits equal to 4.
Okay.
So like 13 would be an example,
Or
right?
22 or something, right?
Or 22 or...
Okay. So, I mean, let's maybe look for patterns. I mean, I think that would
Yeah.
be a way to start is to look for patterns. So positive whole integers. So we're not talking about the number 0, but anything above 0, 1, 2, 3, 4. So counting numbers. And it cannot contain zeros. So, for example, 40 would not work. And
So it's always got to be like once we get like the first digit, like 4 would count, right?
4 would count.
And then once we get to like the tens, the second, like the first number is 1, the second number can't be higher than 3.
So there are only 4 of them. Check it
Only
out.
4?
0, 4, 1, 3, 13, 22, 31, and then
What
40
about
doesn't work.
112?
40 doesn't work. We can keep going. Yeah, you're right.
Yeah.
Okay, so nothing left in the tens is going to work, though, because 50, 60, that's all going to be too high because 6 plus something.
Right.
And then we could get into the hundreds. So we have
112?
100, 103 would be our first one.
No zeros.
Oh, no zeros. Then never mind. This is correct. So 112. And then we have 121.
Right.
And then 130 could work, but again, no
No
zeros.
zero.
So
I think once we're there, that's all we can do in the hundreds.
4, and then there are 2 here. Okay, so what about 200?
Could do
So you could do 211.
211. Yep.
You could do, that's it?
Yeah, I think that's as far as we can
Because
go.
you couldn't do I'm thinking of other digits, 220. That
No,
has a 0 in it. So we couldn't go any higher than that.
And we can't go higher than...
could think about 300s maybe, but
But it's gotta be
310,
301 or
there's
310,
there's still a 0 there. So yeah, all right. So answer is 7. There are 7 of them.
Cool. Nice.
And this, by initially I was thinking this problem, I was like, wow, this could go on forever.
Right.
You never know. But when you kind of come up with examples and a systematic way of coming up with examples, like how we started at 0 and then started thinking of all of our possibilities, then you can maybe narrow down how much it ends up being. In this case,
Yeah.
it was not all that many possibilities, and we could find them pretty easily.
And when you think about that pattern, right, then when we get into the hundreds, if we're like 110 or higher, then we can't have anything higher than a 2 in it.
Right.
So it starts to
Exactly.
like eliminate a lot of options. So yeah, not as many
Very
as we thought.
true. So that was a good one, actually. I thought maybe that would take a lot longer than we
Yeah,
thought.
same here.
Yeah. So,
Do we have
Sam,
time? We can jump back, or
Do you have your?
Yeah, we got a few minutes. I
yeah.
think.
I was trying to pull the diagram to help us, but my computer's being like extra slow.
We can give the trivia question one more time and maybe get it after the trivia question.
Let's give the trivia question one more time.
Okay. All right. So Jeff, what is our trivia
All right.
question?
Well, the trivia question once again is, what is the largest living structure on Earth? And Sam said it's not it's a structure, not a
single organism.
not a single organism. Yeah. So.
All right. Want to answer that one now, Sam, or shall we?
Oh yeah, please.
Yeah.
I'm sorry.
Let's go for that.
I'm
That's
still
okay.
having a hard time pulling up this.
Just making sure.
Pulling up this
I didn't wanna...
image here. I was trying to get the image like all by itself, but we could just jump to my screen really quick. It is not a great picture, but I think it'll give us a sense. So I always have a hard time with the different terms here. I've never really lived around an ocean, so I'm not great with tides. But in general, there are two things that affect the tide on the Earth. There's the sun and the moon. And the reason that the sun and the moon affect the tide on the Earth is that both the sun and the moon are bodies that act gravitationally on the Earth. So we think of the moon as being this really close thing. The moon rotates the Earth once every month. That's why we call them moons, as some people might have called them at one time. But the rotation of the moon around the Earth means that the moon is at different angles to the Earth at different times. And whatever side of the Earth that the moon is on, it's going to actually create a bulge in that direction, or there's going to be a gravitational pull toward the moon. There's also a relatively significant gravitational pull toward the sun. So springtide was one of the options. Was there all the sun and the moon are both acting on the Earth?
Yeah, let's go back to that.
I remember it was a multiple choice question.
Here it is. Yeah, it says, tide that occurs when the moon, sun, and Earth are not in alignment. Tide that occurs when the moon and sun are aligned with the Earth. And tide that occurs during the spring.
Okay, yeah. So the spring months is like a red herring, but so spring tides are alignment, and then the other kind of tide, or the other really important kind of tide, is a neap tide, which is where they're not in alignment. So we can see from this diagram that I've got up on the board, in a spring tide, the moon and the sun both help to create the bulges of the water on Earth, which gets pulled outward from Earth thanks to the gravitational pull of these bodies. In a neap tide, the moon's position compared to the Earth is such that it's sort of acting against that of the sun. So the moon is pulling at a perpendicular angle here to what the sun's pull is. And so essentially in a neap tide, the sun's pull and the moon's pull cancel each other out.
Cool. I think you did pretty well with that. Good job.
Thanks.
I also see some glitter on both of you guys. It's great.
Yeah, I accidentally touched my face earlier, and I was like, ow, disaster.
It's really great. I love it. I love it.
So I guess we should get the answer to the trivia
We
question.
should.
We're
Yes, we
almost out of time
should.
here.
All right. So what's the answer?
All right. Well, the answer to the trivia question is the Great Barrier Reef off the coast of Australia.
Makes sense.
And I got some information on
So tell us.
So it says this stretches on for 1,429 miles over an area of approximately 133,000 square miles. The Great Barrier Reef is the largest coral reef system in the world. The reef is located off the coast of Queensland, Australia, in the Coral Sea. So that's pretty cool.
That is really cool.
Yeah.
That is really cool. Do you guys know anything interesting about
I know
the Great
there
Barrier
is
Reef you could share quickly?
a breathtaking array of marine creatures.
Okay.
So there's actually 600 different types of soft and hard corals, more than 100 species of jellyfish. I didn't know there was nearly even that many in the world. 3,000 varieties of mollusks, 500 species of worms, 1,625 types of fish, 133 varieties of sharks and rays, and more than 30 species of whales and dolphins. There's like quite a diverse population there.
Sounds like a good place to scuba dive.
Yeah, it does.
For sure. Well, we are out of time for today, and this week, really. So if you didn't get your questions answered, or you didn't even get a chance to ask them yet, be sure to send those in to us. over the weekend, and we'll see you next week on Tuesday from 4:30 to 5:30. Thanks for joining us.